B. S is bigger than A, right? S is in AB. Yeah. So S is bigger than A. Certainly T is in AB. So from this, we know that T is a point in this. So it is defined. So we can certainly use this curve to define our solution, because this curve is on AB. Our T is also on the same interval, AB. Yeah, on this interval. So no matter T is smaller than S or T bigger than S, we can define a value at that point, T. So that means this interval, we have a solution, right? We can clearly define the solution at any point on this interval. Yeah, so that's the largest possible interval. Because that interval, on any interval, if it's a interval where there's a solution, it's a subset of this interval. Yeah, so that's the largest possible interval where we can find a solution. But you might have a question. You might want to ask whether I use another solution on different interval, for example, gamma. Yeah, so what if I choose, I have a different interval and a gamma. Yeah, what if, but we don't really worry about whether you choose a curve on a different interval. So as long as you have a solution for given the same initial data, right? Same initial data, we have uniqueness. So it doesn't really matter which curve you pick.
So we have assumed uniqueness, right?
Yes. Assuming you have A1B, A2B, right? They may have different A's, right? With the same B, because there is a solution on the A1B, which called beta. There's another solution called gamma on the A2, from A2 to B, right? But in that case, do you pick beta or gamma? Will that matter? Doesn't matter, because we know uniqueness of solutions, right? Because the condition satisfies the condition for the uniqueness and existence theorem satisfied. So actually, it doesn't really matter. So we have defined a solution. Let's denote alpha with this initial condition. Okay, alpha is defined on the interval of t, time interval, which is defined a solution, which is beta t. No matter t is smaller than s or t is bigger than s, in either case, we have shown that we have defined a solution. Actually, so that's how we define the value, right? On what interval? The largest. This is the notation for the maximal interval of existence, which is actually that interval we constructed. Yeah, we have a defined solution. This solution has a specific value for whatever t, right? so in case you choose a different value gamma, during the process, it will not affect the value because of the uniqueness. So the solution is defined also unique, right? There's no ambiguity. Okay, so we actually gave a proof. So after the proof, I think the notation will make more sense on the notations. So whenever you see this, that's the initial data, that's the curve, right? On the time interval. When you see this, that's the time interval. That's the maximal interval of existence of a solution. Yeah. Yeah, there's a shorter version of the proof. So after we have gone through this proof, the shorter version looks very easy because, okay, let's just take a look at the shorter version. Shorter version of the maximal interval of existence theorem. Yeah, proof of that theorem. So still, method is construct. We construct the maximal interval, right? So we have all the intervals. What do we do? So suppose here is the interval of this form, right? Interval of such forms. And we do union of all intervals of this form. And then we can construct various possible interval. So just do a union of all open intervals. Okay, so let's consider all open intervals I. Okay, we just consider all the open intervals on which there is a solution.
So we'll show that all of the unions will give the maximum.
Yeah, of the initial value problem, right? Yeah, so if we consider all the intervals, so if you have, no matter how many intervals on which you have a solution, then we just do the union of all intervals. So here's all the interval. So we have, of course, a collection of all the intervals, which is I. The notation was defined earlier, right? Collection of all intervals. So whenever you consider the entire collection, you do the union of all intervals of this collection. That will be the largest or maximum interval of existence. Yeah. You see, those are open intervals, and they are connected, right? The union is still open and connected. So it's in R, because the union is still an open connected. Open and connected. Set in R. In order for the set to be connected in R, it has to be an interval. Yeah, so then it is an open interval. That means the union should be an open interval. So we found an open interval actually. So the union of all is still an open interval. Yeah, so next, it's similar to our previous reasoning, right? In the previous version of the proof, we need to show, okay, you give me an interval, then what do we have for every t in this interval? Do we have define the solution, yeah, at the t, at the given t. Yeah, so how do we justify that? So you take any t from this.
Well, you defined I to be
Yeah.
all open.
If t is in this interval, t has to be in,
The union.
yeah, one of the intervals, right? Then you just pick one interval and the solution associated with that interval, right?
Well, T will be in all of them,